Good, good morning. My name is Dwayne Brown with the Office of Communications, and welcome to NASA headquarters. Today, you will hear about the upcoming launch of NASA's Gravity Recovery and Interior Laboratory, otherwise known as GRAIL. Right now, all systems are go for a September launch, and today you will hear the incredible details and science expected. The visuals and information are available on the internet at www.nasa.gov/GRAIL. We'll have brief presentations from our speakers, then open it up for questions starting here at NASA headquarters, our NASA centers, and the phone lines. Before we get started, let me introduce you to today's participants. First up, Jim Green, Director, Planetary Science Division, NASA headquarters, Washington. Maria Zuber, GRAIL Principal Investigator, Massachusetts Institute of Technology, Cambridge. David Lehman, GRAIL Project Manager, NASA's Jet Propulsion Laboratory in Pasadena, California. And Lisa Hubbard, Teacher in Residence, Sally Ride Science, San Diego. And with that, I'll turn it over to Jim.
Thank you very much, Dwayne. With this press conference, we're beginning the launch campaign of the GRAIL mission. The GRAIL mission is a discovery mission for which we initiated the discovery program in 1992. And since that time, we've had 10 launches of discovery spacecraft of various reaches of the solar system. The program has been designed to have frequent access to space for planetary scientists. It's run in a principal investigator mode and a science team supporting the mission and data analysis. Now, to date, the program has done an enormous number of discoveries, and that is continuing on even today. The last year alone, we've had 2 of our discovery missions fly by comets. We've had the Messenger spacecraft get in orbit around our first planet, Mercury. We've had the Dawn spacecraft get in orbit around an enormous asteroid called Vesta. And in fact, most recently, we have selected 3 discovery missions for further study, and about this time next year, we'll select one for flight. The program we're talking about today, the GRAIL mission, as part of our discovery program, will be launched on September 8th is when the window begins. And I'm delighted that our first principal investigator woman, Maria Zuber, is at the helm on that mission. One of the stories I want to tell at this point is when GRAIL was selected in December 2007 and we were preparing for the announcement, both Maria and I were at the scientific meeting in California. And I had the opportunity and the pleasure to go up to Maria and let her know that her mission was selected. And of course, she was incredibly excited about it, and we both enjoyed the moment. But all of a sudden, she got very serious. And she looked at me and she said, "I'm going to promise you right now that this mission will come on budget and on schedule." 3.5 years later, we're now ready for the launch of GRAIL, and I'm here to tell you that is exactly what Maria has done. And so with that, let me introduce Maria Zuber, Principal Investigator on GRAIL.
Great. Thank you very much, Jim. We could start with the first graphic, please. I am so delighted to be here today to tell you about the GRAIL mission. The first image shows just an absolutely beautiful image that was taken by the Galileo spacecraft while it was en route to the planet Jupiter. And if you think about looking at the moon, nearly every human who's ever lived has looked up at the moon and admired it. The moon has played a really central role in the human imagination and the human psyche. If we could have the next slide, please. So much so that when humans reached out and landed on the moon, it really became a defining event for civilization. Since the dawn of the space age in 1959, there have been 109 missions that have targeted the moon. 12 humans have walked on the surface of the moon. We've brought back 842 pounds of rocks and soil that are still being analyzed today. I won't even call it a national treasure, it's a world treasure, those samples. As we speak, there are 3 spacecraft that are orbiting the moon and collecting science observations. Given all of this activity, do we know everything that we'd like to know about the moon? In short, the answer is no. So let's talk about some fundamental things that we know and don't know about the moon. If I could have the next slide, please. So the moon is the nearest, most accessible, old planetary, rocky, terrestrial planetary body. We believe that the moon formed by an impact of a Mars-sized body into Earth, and then the moon accreted out of the material that was thrown off into a disk. But that's a theory. We continue to test that theory. We don't know for sure. Surprises emerge even now about the accretion process of the moon. Trying to understand how the moon formed and how it evolved over its history is one of the things we're trying to address with the GRAIL mission, but also to try to understand how the moon is an example of how terrestrial planets in general have formed. So if you look at this picture of the moon, another beautiful picture, this is a wide-angle camera image of the lunar near side on the left. That's the side of the moon that we see from Earth. And the far side on the right, these images were taken by the Lunar Reconnaissance Orbiter that's currently taking observations right now of the moon. You see that the near side and the far side of the moon are very different. And you would think, having sent many missions to the moon, we would understand the difference between the near side and the far side, but in fact we don't. The near side shows a lot of dark areas that consist of lava flows that flooded large impact basins, which are on the near side of the moon. But this didn't occur on the far side of the moon. And for a long time we thought, well, there was all this magma that was deep beneath the surface of the moon, and because elevations on the near side of the moon were lower, it rose up and we just see it, whereas that isn't the case on the far side. But if we go to the next chart, this is an elevation map taken from the laser altimeter on the Lunar Reconnaissance Orbiter that is still collecting images around the moon right now. This elevation map is color-coded. Here, whites and reds are high, and blues and purples are low. And you see you get quite a different story that begs the question of, well, maybe this idea of the magma being many places on both the near side and the far side of the moon isn't correct. Because on the far side of the moon, on the right-hand side there, you see in the deep purple down towards the bottom, the largest impact basin on the moon. The impactor that formed this basin excavated deeper into the moon than any of the basins on the near side, but no magma flooded in it. So clearly, we don't understand what was happening inside the moon on just the basis of the near side and the far side. Let's focus now on the white area on the far side of the moon, on the right, those highland regions. Okay. Just a few weeks ago in the journal Nature, an article was published that suggested that those far side highlands actually occurred due to a second moon that might have formed after the moon-forming collision that we think happened. This moon would have been in the same orbit as our moon, and ever so slowly, it would have come towards and coalesced with the moon and essentially bumped it and collided. And it added more material to the moon than it excavated, and so it actually produced a mountainous region rather than a hole. The hypothesis that this occurred, it's actually, when I saw the paper, I thought it was outlandish. But as I read the paper, I realized that the simulations that were done were very, very well thought out. And they made specific testable predictions that could be addressed by studying data that will be obtained with GRAIL. The next slide. Next slide, please. Okay, so GRAIL is a mission that will study the inside of the moon from crust to core, and it will use the information that we gain on the inside of the moon along with information that is gained and being gained from other spacecraft that have looked at the surface of the moon and from the continued analysis of the lunar samples. And we're going to show a video next that's going to show you how we make these measurements. So here the two GRAIL spacecraft are in orbit around the moon. They're lined up with each other. The two spacecraft are about 55 kilometers above the lunar surface. The distance between them varies on a large scale between 60 and about 225 kilometers, so we can sample at different depths in the moon. And these two spacecraft will essentially chase each other around in a polar orbit as the moon rotates slowly underneath them. And the basic measurement is that you can see here, as there is a mass on the surface or in the subsurface, the lead spacecraft will accelerate and speed up in response to that mass and cause the distance between the two to increase. And then as the second spacecraft then comes over this greater mass, it will speed up and get closer to the first spacecraft. So we're essentially taking the distance between 2 points and watching how that distance changes. And this is a fundamental measurement that school children learn in middle school or even elementary school when they first take geometry. But the fact of the matter is that we have to make this measurement extremely well. We measured the velocity change between the two spacecraft to a couple of fractions of a tenths of a micron per second. Okay, it's an extremely accurate measurement that has to be made. So if you're out there and you're learning how to measure the change between the distance between 2 points, learn how to do it well, because when you grow up, you might be able to do a mission to the moon. And so I'll pass things over now to our project manager, Dave Lehman, who will tell you how we're going to get there.
Okay, Maria described how we're going to do the science of the moon, and now I'm going to talk about how we're going to get there. And so back when the GRAIL was selected in December 2007, we formed a number of different teams to implement the mission. At JPL, this is where we do the project management, and also the instrument was built for the GRAIL mission. And then Lockheed Martin in Denver, Colorado is where the spacecraft was built, and then United Launch Alliance is where the launch vehicle was built. And so we've been working since then, and in May of this year, that's when we shipped the spacecraft to Florida. And you'll see, next graphic, please. This is an image of the spacecraft. It's 2 days old, and it shows the two spacecraft on top of the second stage of the launch vehicle. And behind that, you'll see this is the fairing enveloping the spacecraft, and we've since put on the other half of the fairing, and we did that in preparations because we were concerned about Hurricane Irene. So the whole spacecraft was all buttoned up and secure if in case we had a problem with Irene. So over the next 13 days, while we're preparing for the launch, a lot of work is going on, the final preparations. The main thing left to do is to fuel the second stage, and then we'll be ready to go. And in the next graphic, I want to show you what we will see on September 8th. This is the launch of the GRAIL spacecraft from the Delta II rocket from Cape Canaveral. And after this first stage is spent, then we go to the second stage of the launch vehicle. And here we show the second stage preparing to deploy the two spacecraft. And then we deploy GRAIL A. And then 8 minutes later, we deploy GRAIL B, and then the two spacecraft are on the way to the moon. What will happen next is a series of maneuvers. We do a total of 33 maneuvers on the way to the moon to get into the proper orbit. And in the next graphic, I want to show you the trajectories we go through. On September 8th, we have that's the opening of the launch period. And we can launch any day after that for 42 days. And on your left, you'll see the trajectory to the moon if we launch on the first day of the launch period. And then in the center, there's a graphic showing how the spacecraft will get to the moon if we launch at the end of the launch period. And so this is a busy time for the team, preparing to get ready for lunar orbit insertion. And then the next graphic will show this lunar orbit insertion. And this will happen on GRAIL A. It happens on New Year's Eve, and on GRAIL B, New Year's Day. And it's a 38-minute burn to get into these orbits. And the orbit period is about 11.5 hours. And so over this period, we do a series of maneuvers to circularize the orbit. Eventually, we want to get into an orbit about 55 kilometers above the moon. And it's highly circular orbit. And this is a period where we go through the transition to science formation. And this is where we have to get the orbits very precisely position so that we can carry out the science phase of the mission. And then in the next graphic, we'll give you an understanding of the data that we collect in order to return to science. We have a K-band ranging system that exchanges ranging data between the two spacecraft, and then we also have another signal at S-band that exchanges the clock information. And then all this data is downlinked from each spacecraft. At S-band is where we send the science data and the health and status data. And then we also have a radio science beacon that returns navigation information for the scientist. So that summarizes how we're going to get to the moon. And let me turn it over to Lisa Hubbard to talk about the education aspect of the mission.
Great. Good morning. I'm happy to be here to have the opportunity to tell you about the education and public outreach component of the GRAIL mission, which is called MoonCam. It's led by Dr. Sally Ride, America's first woman in space, and her team at Sally Ride Science. A unique thing about this is it's NASA's first planetary mission to include instruments that are fully dedicated to education and public outreach. We intend to tap into the excitement of science and technology using the context of lunar exploration. While GRAIL is performing its gravitational experiments, MoonCam will serve as eyes on the moon for Earth students. Give me a slide, please. And how they will do that is through the use of these cameras. Each spacecraft has 4 cameras on board. There are 2 that are looking fore and aft at a 60-degree angle, and there are 2 that are pointed straight down to the surface of the moon using different powered lenses. This program is available at no cost to schools, and students are going to be able to take their very own photos. This is what's going to make the difference. We know there are lots of images of the moon out there, but this gives students their own ownership of that. Once the satellites are in orbit around the moon, the cameras will be activated, and this part of the mission will last approximately 80 days. The mission's operations center, which would be similar to Mission Control in Houston, is located at the University of California, San Diego. There we have undergraduate students who have been involved in the planning, they're involved in the operations of the mission, and during the mission, they will serve as the link to middle school students worldwide. Students are going to be able to access our website, slide please, to help them plan and target the area of the moon that they want to explore further. They'll be able to look at the latitude, the longitude, which orbit and camera will be available for those images. Next slide. This website will also be very interactive. There will be images of the moon that they can rotate, they can zoom in on them, they will be able to view the exact orbital tract of the spacecraft, and they can click on that, and that will also give them information about the latitude and longitude. Once they decide which area they want to explore further, they will send that request to the Mission Operations Center in San Diego. And once the images are taken, they'll be downloaded to a gallery, which will be open to the general public. There will be different ways that those images can be categorized as they begin to build on themselves. Students will be able to go there and access the image that they personally took. They'll also be able to look at other images from other students, and it will help them further their own research by looking at other images. They'll be able to annotate those images, and you never know what a student will be inspired to do with those pictures that are their very own. It might be an artist or a poet or maybe something even in music, which is something that we generally don't think about when we're thinking about science and technology. So both before, during, and after the mission, Sally Ride Science is providing training and support for teachers. We are linking them in workshops with lunar scientists and experts in the field. We are also providing them with hands-on activities they can use in their classrooms that they're already bringing back to their classrooms in preparation. We have over 500 teachers that are already registered on our MoonCam website, and we encourage teachers to go there and register because we will be helping them get prepared for ways that they can use these images as they relate to standards that they have to use and meet in their classrooms. It's really exciting that students are going to be able to do this. Where NASA is just a great vehicle for inspiring students in careers that involve science and technology. Kids have a natural interest in space. Even my 4-year-old nephew calls me and asks me questions about the moon, so he's starting early. We also, like we said, we are going to be engaging middle school students and we'll be engaging undergraduate students. Many of those students have actually gone on to work for NASA by working in our Mission Operations Center. So we hope that this will encourage students in those fields, and they'll be very excited about being part of real-world science, and they will actually be scientists themselves. If you go to our website, www.mooncamucsd.edu, that is where you'll find all the information about the site. We would ask you to tell other educators about it and encourage them to come and register. And I think pretty much everything that you need to know you can find there, and we would encourage you to go check it out, look at the website, and see what's there, and get more involved. Thanks.
Okay, thank you. And now we're going to transition into the question and answer phase. We're going to start here, NASA headquarters with Eric Hand. Then I have some questions that were sent in to me by some of the media that are watching this program across the country, and then we'll go to the phone lines. So, Eric, why don't you start us off?
Sure, thanks, Dwayne. Eric Hand with Nature Magazine. My question's for Maria. Maria, can you explain in more detail how GRAIL could possibly explain this dichotomy between the near side and the far side?
Sure, happy to, Eric. Okay, so we believe that there was melting deep inside the moon, and it could be that there is a mega plume, or was a mega plume in the moon in its far history. And in fact, the Lunar Prospector mission showed that there were high concentrations of elements such as thorium, potassium, that were heat-producing elements. But actually, the Lunar Prospector spectral data only penetrated about a meter deep beneath the surface of the moon. So we actually don't have an idea of what anything related to the composition of the moon beneath that. And GRAIL will be looking at this in many more orders of magnitude in terms of higher resolution. So because of the fact that we will do orders of magnitude better in terms of our sensitivity as well as our spatial resolution. And what I like to say sometimes is that when you can make a measurement better than has been made before by a factor of 2, you make very interesting discoveries. But when you can measure things orders of magnitude better, they can really be paradigm changing. And this is what we're expecting. So we'll essentially be able to look, taking into account our understanding of the bulk composition of the moon on the basis of the Apollo samples and surface spectral data, in comparison with our sensitivity looking at gravity and what that's telling us about the mass distribution radially. We will be able to look at how melting occurred within the moon, and actually what the source materials were that produced melts that occurred to the surface.
Okay, before we go to the phone line, I do have a couple of questions from the West Coast, and the first question is for you, Maria. Question goes, it took the Apollo a few days to get to the moon. Why does GRAIL take approximately 3.5 months to arrive there?
Okay, well, that's a good question. We're using a low energy trajectory that uses the Earth-Sun Lagrange point, and we originally did that to save fuel. Okay, so the Apollo astronauts, we wanted to send them to the moon, get them on the moon, and get them home safely. Okay, and we wanted to do that as expeditiously as possible. But if you think about it, if you go barreling towards the moon, you've got to hit the brakes big time to slow down enough for lunar gravity to capture you into orbit. Okay, that means you need a big fuel tank, lots of fuel, maybe 2 rockets for the 2 spacecraft. Okay, we teamed with Lockheed Martin, who had a very flexible spacecraft that was actually a Department of Defense spacecraft that they got permission to adapt, and it was a small spacecraft. And we wanted to use a small fuel tank in order to do that. So by using this small spacecraft and using the low energy trajectory, it made sense to take this longer 3.5-month trip to the moon. But it turned out that after we got into it and started studying it, there were a lot of other advantages of taking a slow trip to the moon. So first of all, we were able to put those 2 spacecraft into lunar orbit a day apart, so that we're not doing 2 critical orbit insertion maneuvers in one day. We were able to get to the moon on the same day, no matter what day in this 42-day long window that we launched. And that allowed us to completely decouple the operations during cruise from the operations around the moon, which actually greatly simplified our mission operations and one of the things that helped us control cost. Another thing that happens is it gives our operations team time to learn how to operate the spacecraft, and it allows the spacecraft to degas. So the spacecraft within its structure actually has gases that come out, and because even though it's very, very tiny amounts, it's still an acceleration, and acceleration has the same units of gravity. So spacecraft degassing is actually an error source for us, and we have to actually worry about error sources down at the level of spacecraft degassing because we need to make the measurement as precisely as we do.
Thanks, Maria. We're going to do one more question I received from the West Coast, and then we're going to head down to Kennedy. And I think I'm going to ask you guys to get your crystal ball out. Question is, what legacy would you want GRAIL to have, and or its impact to future generations, if you could see in the future? So, Jim, let's just go down the line and individual comments on that, starting with you.
Well, of course, as a discovery mission, it's really doing some pioneering science. And that's what that program's all about. It's well-focused. It has an important objective. That objective is to really understand the evolution and the origin of the Earth-Moon system. We have a number of theories, and GRAIL will set us on the right track of understanding that. Now, that may have application in other parts of our solar system. So its legacy then is indeed applicable to looking at this into the future.
Okay, can I say 2 things? Okay. So one is, the first is when I do an experiment, I like to rewrite the textbooks, okay? And so I think a lot of us, for very good reason, believe in the impact origin of the moon and then the cooling off of the moon and the evolution. I am predicting that we're going to find something, and I don't know what it is, that is really, really going to surprise us and turn our understanding of how the moon and other terrestrial planets formed on its ear. Okay, so that's my scientific thing. But there's also a technological legacy here. So GRAIL is the moon version of the extremely successful Earth science GRACE mission that is mapping the Earth right now, and we were able to take the GRACE instrumentation and adapt it for orbit around the moon. And as you heard from Dave here, it's very important to get precise timing of these 2 spacecraft. And for GRACE does its timing using GPS, but we didn't have GPS at the moon. And so we had to figure out a way to do clock calibrations. And now that we've demonstrated the way that we can do precise timing, this really opens up the possibility of taking a concept like this and doing it around another planet. Say, imagine mapping currents in the ocean beneath Europa using a concept like this. But beyond this particular concept, going to any other planet where you would like to do closely coordinated, timed observations, we've now figured out a way to do this. So I think and hope that the legacies will be both scientific and technological.
I think for me, the big challenge of GRAIL is actually getting into the science orbit. And so we call that the transfer to science formation phase. And it's a very complex phase for us in the mission where we have to get the two spacecraft very tightly coordinated, one around the other. Our navigators are 250,000 miles away from the moon, trying to orchestrate these two spacecraft into very, very precise orbits. And I'm a retired Navy Reserve officer, and to me, it's like the Blue Angels at the moon. And so that's our big challenge, and we're really looking forward to doing it.
Well, I can only speak to MoonCam, but I think that is going to impact students in an emotional way as well. While the moon is our nearest neighbor, there is still so many things that our students don't understand. It may be the first time our students realize that the dark side isn't the same as the far side. And I think once they begin to look at detailed images, when they go out in their backyard and look at the moon, they're going to look at it in a whole new way. And I think that's priceless.
Excellent, thank you. Okay, now we're going to head down south where the spacecraft is preparing, getting made ready for launch, and we're going to go to the Kennedy Space Center there for a question or two. Kennedy, how do you read?
Hear you fine. This is Marcia Dunn of the Associated Press with actually 3 questions, if I might. For Dr. Zubrin, could you give me some sort of a reference point? You were mentioning the precise measurements that will be taken between the two orbiting craft. I think you mentioned 1/10 of a micron per second. That's hard for me to imagine. Could you put that in some simple terms that I could explain to my readers?
Sure, it's about half the size of a red blood cell.
I'm sorry, could you repeat that?
A 1/10 of a micron is about half the size of a red blood cell.
I'm sorry, you're breaking up. Can you try one more time?
Okay. Half the size of a red blood cell is a 1/10 of a micron.
Okay. Got that. Second question, probably for you, or maybe Dr. Green as well. Are there any implications from your results that you anticipate that might be able to benefit future human explorers, astronauts who may one day want to live on the moon?
Yes, I'll answer that. GRAIL was selected in our discovery program from purely scientific reasons, and it has important implications for the origin and evolution of our solar system as we've discussed today. And of course, that data will always be available. We'll be developing models, we'll be putting that in the archive, and it will be available for future generations and future missions, which would include potentially human exploration missions to the moon. So how they use that will be dependent upon their decisions and what they want to do relative to landing and exploring the moon further.
Yeah, if I could just add to that. So this will be the highest resolution gravity field for any planet, including Earth. Okay, on Earth you can't get down low enough to make the kind of measurements that we're making because of the atmospheric drag. And actually, atmospheric drag is another force that needs to be contended with because it has the same units of gravity. You can't. It's very difficult to separate that out, so you can't map that low. So, the ability to do precise targeting of observations by humans or by future robotic explorers is going to be really unprecedented after this gravitational field is produced.
Thank you. And my final question, probably for Dr. Green, or maybe Dr. GRAIL as well. There was immense attention on the Juno mission recently, given the end of the shuttle program. And I'm wondering, do you anticipate a more interest than usual, more attention, more eyes on the launch of GRAIL coming on the heels of Juno and the end of the shuttle program?
Well, I certainly hope so, in the sense that our planetary program that NASA has, that this country pays for, is really unbelievable in terms of its ability to enthuse our students and engage the scientific community of the world, And I'm just delighted that the country is responding by now, beginning to look, going down to Kennedy and being able to observe the launches from Kennedy of our robotic spacecraft. Juno, you mentioned, was the first robotic spacecraft launched after the shuttle. GRAIL is the second. And we certainly are anticipating a large crowd attending the GRAIL launch when the window opens on September 8th. So we're just delighted by the way the country is responding to these exciting missions.
Thank you, Jim. Let's go to the phone line, and we have on the phone Anna Ketchum from the Harvard School of Journalism. Anna?
Hello, hi. Thank you. I wondered if both Dr. Zuber and Ms. Hubbard could address this question. I see that you can register for the Moon Cam if you are abroad, if you're a teacher abroad, and for the young students worldwide. And I wondered if you could speak to why it's important to reach out to teachers and their young students worldwide while at the same time reaching out to American students. Why are we reaching out abroad?
Well, we have a similar program called EarthCam that we have always had students worldwide that have participated in. I think the International Space Station is a perfect example also of why it's important that we are all working together.
Maria, did you want to add something to that?
Yeah, I think the moon should be for everybody. Everybody looks up and sees the moon, and I think that the more that brings us together as opposed to draws us apart is good for everybody.
Okay, we're going to go now to Irene. Irene, are you there?
Dwayne, yes. I was wondering if someone might just discuss a little bit more detail about how you're able to make that precise of a measurement, and also if there's any relation to that new technology demo mission that was just announced to fly an atomic clock, a deep space atomic clock. Thanks.
All right, so I'll talk about the things that we have to do to make the measurement at that level. So we have a radio system that is at a very high frequency, so that's a good start to make a relative measurement. But we have to make incredible corrections to be able to figure out where the two spacecraft are and what the relative timing of the two spacecraft are. So actually our biggest source of error in the measurement is the pressure of sunlight on the solar panels, which we have to calculate and correct for. We have to take into account the masses of all the planets in the solar system. We have to take into account corrections due to general relativity, which is a very, very small force. We have to make corrections for the weather at the sites where we have tracking stations on Earth, so making corrections for things like the ionosphere. And we even correct for the tectonic drift of the plates that the radio tracking antennas are on. So, so to be able to make a measurement that precise is just an absolutely, it really takes an extraordinary amount of work. So obviously, GRAIL is a mission where you won't be able to log on to the website every day and see a brand new gravitational result because of the immense amount of processing that goes on with this mission. But when we produce the products, it'll really be spectacular, I think.
Okay. And just for clarification, that was Irene Klotz, who writes for Reuters and Discover and other publications. So thank you, Irene. Our next question is from Mike Wall from space.com. Mike?
Oh yeah, hi. This is a question about the launch, I guess, and what you guys have had to do to prepare. Could you just speak briefly about what the big storm has kind of done to your preparations, if it's affected them at all, and if you're anticipating any other kind of impacts from Hurricane Irene.
All right. When we heard about, I first heard about Irene about last Sunday, and we quickly decided we have to get ready for this. And so what we did is we moved up our schedule a couple days, and we actually put the fairing on the launch vehicle a few days ahead of schedule on Tuesday in order to prepare for this. And then we instituted our hurricane plan and made all kinds of preparations, and it's looking like that we're going to be okay, and it will have no impact on the GRAIL mission.
Yeah, I should say our colleagues at ULA who are taking care of the launch vehicle and down at KSC have just, they added extra shifts in the work to get all this done to make sure that they could secure the spacecraft. And so we've had really amazing help from KSC and ULA on this to really get this. I feel very comfortable that the spacecraft are going to be safe during the storm. I worry more about whether I'm going to be able to get from Boston down to Cape Canaveral early next week when I'm supposed to be down there.
Well, thank you. And that's going to do it for us today. All systems are currently go for launch in September. Again, go to www.nasa.gov/GRAIL for the latest developments and information on the science. Thank you for joining us, and we will see you down in Florida in September. Have a great day.